and other universities and national labs. And then I'm going to talk about the technologies we're working on for electric drive components. And I will finish my presentation with a few slides on what we're thinking now, mainly in the medium duty, heavy duty vehicle space. That's the new target for us. So for those of you who might not know where Oak Ridge National Laboratory is, we are actually close to North Carolina, actually 5-6 hours from here. And Atlanta is 3 hours, Nashville is 2.5 hours, Cincinnati is 4 hours. So we're in a central location in Knoxville, Tennessee. Actually, the main campus is Oak Ridge, Tennessee, but I'm going to show you the building I work on. Actually, you see it in the background. That's the National Transportation Research Center. That is in Knoxville, only around 10 miles from the main campus. So this is the way the campus looks like right now. Whenever I hear my bio, I realize I've been at the lab for 20 years. So when 20 years ago, this campus didn't look anything like this. We had also World War II buildings, but now it's a great looking campus. Of course, I'm on campus right now, but that's not where I usually work. I work at NTRC. So there are 17 national laboratories, and Oak Ridge is one of the largest one. There are other DoD national laboratories and national labs for other agencies, but 17 of them are just for DOE. A $2.5 billion budget is where we are right now. I think we're going to $3 billion. We have more than 500 employees, and we're hiring a lot of senior folks in the last 6 months. So our numbers will grow. And we also get research guests every year. This can be for a week or 2 weeks, a month, 6 months, a year. It depends. And we work closely with the universities, students, professors, when they come visit us and work with us on our campus too. So a couple of interesting things about the laboratory. A few years ago, we had the world's fastest supercomputer called Summit. Now I think it's the second or third. I know that the next one will be named Frontier, and it will be the fastest supercomputer in the world, probably in a year or two. So, this one, the Summit, was actually designed for AI applications based on GPUs, and it was built to make sure that AI applications run as fast as possible. And also, even though I wasn't involved in the work here, Tennessine is the most recent addition to the periodic table. So I guess if you buy a most recent periodic table, you will see TS there, and that was that was actually discovered by the Oak Ridge National Laboratory, Vanderbilt, and University of Tennessee, if I remember correctly. So with that, they were able to name it after the state. So this is National Transportation Research Center, the first building. And then second building is Grid C, where we have 1 megawatt power capability right now, looking at extreme fast charging, wired extreme fast charging. And the third building is the manufacturing demonstration facility, where we can almost print anything. Plastics, metals, a lot of things you can think of, or you cannot think of, that can be printed here. And this is my office here, the third window here, and this is usually my pond after a rain. Right now it's dry though, it hasn't rained in a few days. So when you look at the power electronics and electric machinery research at Oak Ridge, there are more than 30 people. We're not all working on transportation applications. As I mentioned, we have up to 1 megawatt power. So we're looking at renewables too. We're looking at grid systems, transmission, distribution level work, all power electronics, and also other studies in the power systems area. So we have more than 700 square meter lab space. Actually, it's almost double now if you consider the new building with the charging capabilities there. So we have a lot of space and a lot of work going on right now. So over the years, we developed capabilities to be able to start from the chip level. My group doesn't do chips, but we buy the chips from different manufacturers. We package them, we put them in DC-DC converters, inverters, and we can evaluate them in-house. The same thing with electric motors. My group doesn't work on steels necessarily, but we can we can design laminations, get the laminations cut, punched, and then actually build the stacks of stators, rotors, and build the whole motors in-house and wind them, and then actually evaluate them all in-house. So it's good to have that capability. Whenever you want to propose something, you have a new idea, it's good to have these things so you can go through from the chip all the way to the system level. So looking at the consortium, we started working on a roadmap around 2016. It took us almost a year to come up with the roadmap for this. This is something we do usually. For this one, we had the US OEMs involved under a program called US Drive, and we had DOE and multiple national labs. So working together, we noticed what was happening where the current vehicles in 2016 or 17, this is the Chevy Bolt, they were more or less imitating what the gas vehicles looked like, so putting everything under the hood. And then we noticed that the trend was to go to these skateboard designs. By the way, just to let you know, this photo is for a 2001 vehicle chassis by GM Autonomy. So actually, this was something that wasn't just thought in 2017 and beyond. This was actually an idea that was developed by GM engineers years ago. So we said, okay, if everyone is going to go to this skateboard design, where you have really a thin skateboard with the batteries, you need to be able to put the motor and the inverter in here so that they won't look out of place. They can be more or less integrated into the same body. So with that, we said we need to focus on the power density. So looking at that, compared to 2015 targets, you can see our 2025 targets here. Cost-wise, we're looking at half the cost compared to 2015. And power density-wise, almost 10 times, actually 8-something times the power density, which is really challenging. Power level-wise, we used to work at 55 kilowatts, but with the higher power hybrid electric vehicles and then plug-in and then the battery electric vehicles, we said 100 kilowatt might be more relevant these days, or at least in 2017. And when you look at the reliability and lifetime, we used to look at 150,000 miles. Our new targets say 300,000 miles. Now, if you're interested in all these decision-making points and targets and goals in more details, I have the link here at the bottom where you can click and read the roadmap to get more information. Having said that, today, actually, we are working on the next roadmap. It's not final yet, but with that roadmap, we're going to be looking at 2030 targets and goals. So what do these numbers mean? So if you look at the 2016 BMW i3, here are the motor, liter, inverter, and traction drive volumes. And when you look at 2015, the numbers are pretty similar, 2020 and 2025. So for the motor, we need to go from 11 liters to 2 liters. For the inverter, from 5 liters to 1 liter, and for traction drive, from 16 liters to 3 liters. So just in case you're interested, for the inverter, we're looking at 100 kilowatt liter power density. For the motor, 50 kilowatts per liter. And for the drive, 33 kilowatts per liter. So these are really challenging. So we have to look at these different technologies, and sometimes look at technologies that are, of course, not being used right now for a reason. The manufacturers don't find them maybe ready yet or too expensive, but we need to look at them right now to see if they are manufactured well, if there is enough demand, the cost of these things can go down. So when you look at the consortium membership, you're going to see the 4 national labs. Ames Laboratory looks at the motor materials. RNL does thermal management. Sandia is mainly focused on silicon carbide and gallium nitride devices, but they have some projects on the inverter side, motor side, and the integrated drive side. And as Oak Ridge National Laboratory, we are mainly on the system side. So we're looking at packaging, inverters, motors, integrated drives. And my slides after this will show some of the work we're doing in that area. You see 10 universities, NC State is here. PowerAmerica, NC State is a big part of this. There are a few industry members with seedling projects and a couple more universities you see over here. So we started this, I guess this is the 3rd year. So we have 2 more years, a 5-year consortium. So we have 2 more years to go forward. And if you're interested in more of the consortium, you can also look at this presentation from Mr. Steve Boyd of DOE. There he talks more about this consortium and the other work that's being done under the electrification portfolio within DOE Vehicle Technologies Office. So when you look at it from the RNL point of view, what's our approach? So we are working with, even though we have more than maybe 20 organizations in the consortium, and we're working with them, but we are working closely with some of the others. We form these projects where we're expecting different parts from different universities and different national labs to to go with our inverter designs, motor designs, and integrated drive designs. So when you look at it, we're Sandy, as I mentioned, they're looking at silicon carbide and gallium nitride power devices. So we're hoping at some point before the end of the consortium, we will get those devices so we can put them in our modules. The modules we're developing with University of Arkansas and Virginia Tech. So we're looking at different aspects of the power module so that we can put them all together and build an inverter. Today, actually, we are in the process of building a 100 kilowatt inverter that would meet the 100 kilowatt per liter goal. We're planning on building it by the end of the fiscal year, which is end of September. And next year, so we can evaluate and see if we can go to the next generation or next iteration of this inverter. On the motor side, we're working with Ames National Laboratory, and they are working on materials. So we're going to use those materials or, some of the advice we get from them in our electric motor designs. And then we're going to integrate the inverter and motor into the integrated drive. So I have a lot of slides on different parts of different projects we're working on, but I don't have the latest and greatest of these things because I didn't want to spoil the surprise for you, because we have what we call an annual merit review coming up at the end of June. You can go there with this link. The slides will be available later, so you will get the links and go to these websites. I highly recommend, if you're interested in these technologies, to connect, to register for this. I think it's $50 registration for this virtual merit review, and this way you get to see the latest and greatest of all the work we've been doing. But if you're interested in the past work, you can still go to that website, and then you will see this link, merit review presentations. And when you go through there, you can find our presentations or project updates for the last 10 years. So you can see the evolution of all the projects we're working on. And you can see what has changed over the years from a focus on fuel cell hybrids, plug-in hybrids, and battery electric vehicles. And not just electrification components, even if you're interested in fuels, engines, vehicle systems, smart mobility, you can find presentations in all those areas in this database. So now I'm going to go into more of the projects, talk about more details. So we have 3 Keystone projects I mentioned. The first one is the highly integrated power module. And the PIs for this are Guja Su, Emre Gurpuner, and Sajat Chowdhury. So the slides you're going to see, I got from them. And at the bottom, I usually put their names and their email addresses. You're welcome to contact me for any of these things, or you can contact them directly. Either way, it's fine. So when you look at the components of an inverter, this is a slide I put together maybe more than 10 years ago, and it's still valid for some of the components. The challenge is this: we have all these different components, and then we have to stick them together, and there's a lot of air in between. And if you look at the components occupying volume in an inverter, air is occupying out of volume. Basically, we're trying to reduce the amount of air that's in the inverter. So if you look at it in a different way. So when you look at this, the highest volume components are the capacitors, heat sinks, power modules, and then we have of course, controllers, gate drivers, sensors, bus bars. Sensors is something interesting because a few months ago, I looked at the sensor volume. If you get discrete sensors like this, they still occupy out of space, even though, we've been using them for so long, there has been a lot of progress. So you're going to hear that, for example, what we're doing is we are trying to integrate more of the sensors, more of the gate drivers inside the power module, working with the other universities. So there's more integration we're working on, integrating more of the components into the power module so that we can reduce everything, reduce the size of the inverter. And we're even looking at, for example, you see here the heat sink, and then you have the power module. What do? We put the power module on top of the heat sink because they're 2 different components. What if they were the same component? So we're looking at eliminating layers and integrating more of these components together. So let's look at the power modules. So how do we reduce the volume of a power module? We're looking at efficient and flexible substrates. We're looking at different interconnects, not just wire bonds. Of course, double-side packaging is everyone's looking at. Some of our approaches at RNL right now are single-sided, but we're working with others. And then eventually we're going to move into double-side packaging because we're looking at substrates right now, and there's no need to go to this double layer. But there are other universities and other entities who are working on that in the consortium. Gate drivers. So can we reduce the size of the gate drivers, especially having low-profile gate drivers where you have we don't have the transformers or possibly capacitors sticking out? Can you make them as flat as possible and maybe integrate them inside the substrate? So integrating gate drivers, controls, and sensors are all things we're looking at. So on this is something we're doing at RNL, looking at the substrates. As you know, today, everyone is using DBCs, all the commercial power modules. They're using direct bond copper systems, which are basically copper at the bottom, then you have a ceramic, and then you have copper on top. And this is how you connect the die. You basically solder them here, and then you have wire bonds. If you don't have wire bonds, if you have double-side packaging, you have to solder from the top to from the other side. So what we started looking at a couple of years ago is insulated metal substrates. They are being used for low power applications. They are flexible. They can be low cost, but their thermal response is not as we expect. So, if you want to scale them up to higher power applications, higher power modules, we need to improve their thermal response. So working with a few companies listed here on the right bottom, they have a technology called TPG. So that's the thermal pyrolytic graphite. I used to have a hard time remembering all these things, so that's why I had to spell them out. So at least I have the cheat sheet over here now. So when you integrate this graphite inside the substrate, you can improve the performance of the overall substrate. So that's what we wanted to look at and to see if we can actually use IMS in power applications. So we developed 3 different substrates, one with DBC, one with IMS, the other one with IMS and TPG. So, and then we had our setup. You see the die here on top of the substrate and all the wire bonds, everything is connected. That's on the other side of PCB. You have the gate drivers, everything in this. And then you have the capacitors. And with some thermal cameras, we looked at the thermal responses of these things, and we evaluated the overall operation of these thermal systems. So when you look at the charts over here at the bottom, you see the thermal resistance here. This is for DBC, this is for IMS, this is with IMS with TPG. As you see here, RTH, we were able to get lower RTH in these cases compared to the other approaches. So there's a possibility for us using this for high power applications. Doing more work, looking at heat spreading and looking at transients, we were able to see that actually we have a 10% improvement in current density. So basically we can send 10% more current for the same volume. So this is all promising. This is a promising technology that can be used for these applications. We also started working on, in the past year, something called ODBC, Organic Direct Bonded Copper System. That's a technology developed by DuPont. So we're working with them. We designed something with them. We're looking at, basically with them, you can have multiple layers so that we can integrate maybe the gate driver inside these. And then there's a way they can build all of these things over a heatsink. So we can have a more integrated power module like this. So they're supposed to send us the prototype, I think, this month or next. So we won't have the results for that in June, but hopefully next time I present it, we'll have more results in that. That's another substrate we're looking at to replace the DBC. Now, another, of course, high volume component is the heatsink. So for the heatsink, some of you might have heard of our genetic algorithm optimization of heatsink. Actually, maybe a month ago, we gave a webinar, IEEE PELS webinar. I think it should still be available if you're interested in hearing the details on that. But with this, what we're looking at is we have two objectives. We're trying to keep the junction temperature or the highest junction temperature. For example, if you have these 6 die, the highest junction temperature of these things to be less than 110 degrees C, and the maximum pressure drop to be less than 1,000 pascals. So with that, we can design these different heat sinks and then pick the one we are interested in. For example, if you run our tool, you see these dots here? These dots are all solutions that are still below the temperature limit before the pressure drop limit. These things. So depending on the application, for example, if you want a lower volume and we don't care about the pressure drop, then we can go with an with a heat sink like this. This is the leftmost volume. Here is the design for that. Or we really care about the pressure drop. We want it as low as possible, but we don't care about the volume. We can go with this dot over here, and that will be this design. You see, the volume is a lot larger compared to this one. Actually, it looks double in this case. So, and actually it's 0.7 to 1. It's almost double. So, or else if you want something, you know, if you want to trade off some pressure drop and some volumes, you can pick somewhere here, then you will get a design like this. The interesting thing about this, actually, we had a postdoc who worked with us last year. Originally, we had a student working on this. He had different ways of optimizing this, but our postdoc, Raj Sahu, came up with this idea of using Fourier series for designing this profile. So this profile, what you see here is, you think of the flow going inside the screen, into the screen. So as the flow goes in, with the surface area we have with these spiky fins, we can cool the devices so that, you know, we can keep the temperatures to be below a certain value. So it was a clever method to actually design these heat sinks. So since you can create any kind of waveform, you can create any kind of structure over here. So for our application, we compared these to BMW i3 from 2016, because we used to be able to do benchmarking of these technologies. And the last one we were able to do was the BMW i3 from 2016. And compared to that technology, which uses a pin fin heatsink, we can reduce the volume by 50% and the mass by 48.5%. This is a very interesting tool in the sense that, you know, you just put in your design over here. Design meaning, you know, which chips you have, where they're going to sit, you can give the dimensions to it and the losses on these chips, and then you let the tool run for a few days and then come up with this design for you. So it takes a few days, but I think it's a lot faster than someone trying to design something like this. Then looking at the capacitors, if you want to reproduce the volume of the capacitors, things to look at: high energy density capacitors. So I'm going to talk about ceramic and ceramic capacitors a little. Now, when I read some papers, I see people are still talking about electrolytic capacitors for electric drives. We don't use them in traction applications, and we haven't used them. I have never seen, actually, since I started working in this area, I haven't seen electrolytic capacitors being used. You have a lot of issues with electrolytic capacitors, and the volume, I don't think, will be something that will help you here. So we're looking at different high energy density capacitors that are not being used in traction drives right now, but they are the ceramic and ceramic capacitors. We're also, right now, if you see capacitors, you're going to see they are in a block. They are potted in a block, large block, and the capacitors usually take around a third or a quarter of the volume. So they are pretty large. We're also looking at power electronics topologies and looking at ways of cooling capacitors so that we can reduce the size of them. So these are different technologies you see over here. Again, we're comparing this to BMW i3. So if you look at the BMW i3 capacitor, it's a little more than half a liter volume. If you look at the latest and greatest film capacitor, and then if you redesign the BMW i3, you're going to get, again, closer to the volume they have now, a little tad bit smaller. Then there are the ceramic capacitors and PLZT or ceramic capacitors. So as you see here with ceramic capacitors, you can get, for the same capacitance, you can reduce the size of the capacitor by 81%. For ceramic or PLZT capacitors, it goes down to 76% reduction. So we are not going to pick the ceramic capacitors for this. You might think, okay, well, ceramic capacitors have the lowest volume. Why not pick them? Now we're going with the ceramic capacitors. The reason for this is this. So the way I understand is, think of it as a sandwich capacitor, right? You have the metal on one side, the metal on the other side, and you have ceramic in the middle. So in case of a failure, the way I understand is ceramic fails, cracks, and then the metal can short. So when if the metal shorts, that's not a good thing in a vehicle. That's one of the reasons the OEMs, the car manufacturers, have been avoiding ceramic capacitors, and they have been looking at them. Now, PLZT capacitors, on the other hand, they have a similar structure, but instead of just a ceramic in between, they have a polymer with ceramic. I think there's some kind of a composite. So with that, even if you have failure, the polymer will not let the two electrodes short. So that's why the failure mechanism seems to be better for PLZTs, and that's why we're going to look at these PLZT capacitors. Now, there's also something interesting too with the film capacitors. You've probably seen film capacitors around. You have sheets, and then you roll them into cylinders. With these PLZT capacitors, these are tiny chip-sized capacitors, and you have to parallel a lot of these things to achieve the DC capacitor values we need. So packaging of these capacitors is a big deal. So we looked at different ways of putting them together. There's the flat design on the right side, but something when you go with the flat design, you see over here, if you look at the current distribution, or if you look at the thermal distribution, you're going to see that they're not going to be sharing the same currents, and some of them will be hotter than the others. So that's not going to work out. So we said, okay, let's look at a different way of packaging them. That's when we thought of circular packaging, circular design, where we can align them properly so they can share the current better, and they have lower parasitic inductances so that they won't impact our switching. There's another interesting thing for these capacitors. They have a positive temperature coefficient. As one heats up, it pushes the currents to the other. Actually, paralleling them is not that bad. All you have to do is make sure that you have the same current going through them, so that thermally they won't have to do this cycling all the time. So actually, we have an enhanced version of the circular design, which we'll be talking about at DMR. Sajjad Chowdhury is the PI, and he'll be talking about that. So as I mentioned, here some challenges and opportunities. Failure mechanisms, they are a challenge, and even though I mentioned to you what PLZT capacitors, how they're supposed to fail, we haven't done a lot of failure mechanism work. We don't know exactly. We haven't failed them, so that's not. I guess it's a good thing too. But we need to make sure that when they fail safe. And there are still concerns about the cost of these things and only a single supplier producing them. But the way I think of it is, 20 years ago, we were working on silicon carbide. We started working on silicon carbide devices. We had a project then, and everyone's saying these are too expensive and they're not going to be used possibly. But now we see, they are already in vehicles, and PowerAmerica is doing a great job, making sure these devices are everywhere. And a lot of applications use these silicon carbide and gallium nitride devices. I mentioned paralleling is an issue. So just as a reference, we need let's say, some of these things are at 1 microfarad. For a 450 microfarad DC capacitor, we have to parallel 450 of them. So those are the numbers we're looking at. I mentioned distributed capacitors. The circular design I showed, actually, we're designing them per power module. So I'm going to talk about the segmented inverter a little later. Segmented inverter has 6 phases. So with that, we're going to have a single circular capacitor packaged per power module. These are tiny. So this way we have distributed capacitors, and there's a possibility we can cool them better too. So here's the segmented inverter you see over here. So this is another way of reducing the size of the capacitor, right? If we have the segmented system with twice the ripple current at the DC link, and twice the frequency of the ripple current in DC link, we need only half of the capacitor. So my colleagues at the lab, actually I don't have a name, but Dr. Gujasu is working on this, and this is his invention, his design, and he's telling me that we can reduce the volume of the capacitor up to 60%. So it's all because you see here with the reduction in the ripple peak, we can achieve that. So another advantage of these segmented inverters is that here we have it almost looks like a 6-phase system, 6-phase motor. This doesn't mean that the motor is more complicated. You just have to make two sets of 3-phase windings. Instead of connecting them internally, now you're connecting the inverter, and then you're switching them through the inverter. So this system also allows you to have more fault tolerant operation. And one more thing, you might not have noticed this. I started last year or so, I started looking at more medium duty and heavy duty vehicles. And when I look at those, they are actually using 6-phase and 9-phase inverters and drives. I think the main reason for that is they don't have power modules or inverters at these higher current ratings. So instead of paralleling power modules or paralleling devices, they're just using multi-phases. So this is an approach, and it has a lot of advantages too to be used. Now, something else I want to highlight here, 800 volt plus. So with the consortium, today actually before the consortium, if you looked at the DC link voltages, you saw probably 325, 450 volts. That's the battery voltage. With the hybrid systems, you used to have the boost converter that would increase the voltage to 650, 700 volts in Toyota systems. But for this all battery electric vehicles, we're pushing to 800 volts plus. So that means your 1200 volt devices would be needed for this. And 800 volt devices, so we have lower currents. So of course that also helps us with the size of our drive too. And higher voltage, lower current is always beneficial, and this is a great place for silicon carbide devices to excel too in the higher voltage case. Eventually gallium nitride devices would be here too, but I think today silicon carbide has a good place for 800 volt plus designs. Another reason for 800 volts is because we're going after extreme fast charging, which is 350 kilowatts and beyond for passenger vehicles, and maybe going beyond 1 megawatt for medium duty, heavy duty vehicles and trucks. And again, current becomes an issue, right? So 800 volt charging with 800 volt batteries will help you eliminate the boost converter and reduce the amount of current you need. So you don't need a boost converter to connect to the charger. You don't need a boost converter to connect to the motor and the inverter. So that's the advantage of going to higher voltages. So in the second Keystone project, which is on motors, we looked at different motor topologies, looked at high fidelity modeling to improve the optimization of these motors, and also ultraconducting copper, which is an interesting concept coming from the materials side. So at the beginning of the consortium, we wanted to have a portfolio of motors, and we wanted the OEMs, our partners, our car manufacturers, to look at these designs and pick the ones they're interested in. So my idea was the auto rotor motor, because that's something we hadn't looked at. And I missed that meeting where this was discussed with the OEMs, but at the end, I was happy to hear that they picked the auto rotor motor because they hadn't worked on that either. This motor here is what they picked. They were interested in that. They want to see what can be accomplished now with this. So then, because of that, we started working on the auto rotor motor. So one of the advantages of the auto rotor motor actually is the stator is in the middle. You have the rotor outside, and with the stator, it's stationary, and you can have a hollow space in the middle where you can put the inverter. So for this consortium, my idea was, how can we integrate the inverter into the motor? Can the inverter be a part of the motor? And if you can integrate the inverter inside the motor without increasing the size of the motor a lot, then you're also saving volume too. So I'm going to talk about integrated drives right after this. So this ultraconducting copper project, we worked on for a few years. and we had some results, but the funding situation is all, we're low on funding right now. There's a pause on this project. Now, my understanding is the Department of Energy is really interested in ultraconducting copper, not just this project, other methods too. So there might be a program in this area looking at how we can get higher conductivity. I don't want to say metals, it could be composites. In this case, for example, we have a copper tape. We spray carbon nanotubes on top, and we have to align them and just spray on top of them. And if you wanted more layers for higher current, we can actually put them on top of each other and come up with multi-layer architectures. The whole idea is, can we have the current, some of the current go through carbon nanotubes as opposed to copper? So if you look at the electrical and thermal conductivity over here, if we have a lot of the current going through carbon nanotubes and less on copper, we can improve the conductivity. For this small amount of funding and small project, we were able to improve the conductivity by up to 6% compared to copper. But I want to see, what the impact of this would be on electric motors. So there's a paper that was published by my colleagues here, looking at if we increase the conductivity of copper up to 100%, how much of the motor we can reduce. As you see here, we can reduce up to 10% reduction with 30% improvement, and at 100% increase in conductivity, we can reduce the wire by 30%. So there are some advantages. Of course, ultraconducting copper is not just for motors. Bus bars are still important. Bus bars, the higher conductive they are, the better. Of course, if we could find the material that's really highly conductive, highly electrically conductive, and highly thermally insulating, that would be even better, so that our power modules will not be heating the capacitors. But still, we're trying to get to higher conductivity materials. So on the third Keystone project, the integrated electric drive, over the years, people have talked about integrated drives. Every now and then I would get an email from DOE or some others say, hey, look, this company came up with an integrated drive. And when I look at those, this is what I would see. They have the motor and they put the inverter right on top. There is no integration except for on the thermal side. So this is not the kind of integration I had in mind. So we said, okay, what can we do? So these are different approaches we came up with. So we're looking at, as I mentioned, with the outer rotor motor and integrating the inverter right in the middle. It's very challenging, but that's what we're looking at right now. In the consortium, we also have University of Wisconsin. They're looking at the axial stator mount. They have also experience in those kinds of motors. So they're looking at that. And something else to mention here, outer rotor motors, NC State is also looking at it. Iqbal Hussain, Professor Hussain is looking at outer rotor motors too. So it's good to have these, multiple parallel approaches. We don't have a winner in these consortium. We want to look at different technologies and see which one works the best for us. So if you look at the outer rotor motor here, as I mentioned, the electronics actually inside changed since I prepared this slide. But again, I'm mentioning to you at the end of June, we're going to have those AMR slides. If you can attend, you can see the latest and greatest on these. And also, if you cannot, those slides will be available at the link I'm going to share on these slides. So last few slides, I want to talk about medium duty, heavy duty electric drives. So the way I see it right now, there are electric vehicles in the streets, and there are more coming up. There are not too many medium duty, heavy duty electric vehicles, and there's a push for it. You've probably heard in the news that the new administration is pushing for all the government vehicles to be electrified. I don't know what that means right now, but think about the postal mail vehicles. They're going to be electrified. Trucks, again, they will be electrified. But that's not just the US government. We're also seeing the OEMs, car manufacturers, truck manufacturers, bus manufacturers. They're all looking into electrification and how they get there. So I wanted to highlight the difference here, because now our focus is starting to be these MDHD systems. So I need to know from the program point of view, what's going to change. So there's also another partnership called 21st Century Truck Partnership with the US OEMs, we're trying to come up with another roadmap, this time for these MDHT vehicles. So I talked about 800 volts. Now we're seeing possibly 1,000 or 1,500 volt batteries in these trucks. The reason for this, as I mentioned, of course, if you go to higher voltages, lower currents, but also charging. We don't want to have any boost or buck converters in the middle. Higher cost, reduction in efficiency. So when you look at current standards, which are trying to work on standards for charging of these medium duty, heavy duty vehicles, they're looking at 1,000 volts to 1,500 volts flexibility. So you can have 1,000 volt battery or 1,500 volt battery. I want to get to 1,500 volts because that's what I'm seeing in solar area and other areas. Higher voltage helps us. Now, but there's a difference when you look at the power electronics side, right? If you're at 1,000 volts, then 1,200 volt devices will not be ready. It will not be good for it. So are we looking at 300 volts? That seems to be too much of a margin. Maybe now we need another class of vehicles somewhere in between, class of devices, somewhere in between 1,700 volts and 300 volts. That's a possibility. Or looking at new traction inverter topologies, like in multi-level inverters, they could be a solution for this. Of course, if you do that, we need new power modules. We don't need phase legs for the multi-level inverters. I think there are other basic modules we can come up with that will help with the multi-level systems. Higher voltages mean high voltage insulation materials, high voltage capacitors, new dielectric materials. Those are also big issues. Now, 1,500 volt DC. Then if you think about it, we need to go to really higher voltage rated devices. So something to think about, something for PowerAmerica to think about too. So higher current levels, of course, do we parallel more devices or we do 6 or 9 phase materials or higher number? What's the best number for that? And of course, other higher conductivity metals or composites will also be of interest. Another interesting thing is durability. For passenger vehicles, I mentioned 300,000 miles. Well, for trucks, they want to go to 1 or 1.2 million miles. And our devices and our inverters, motors are not ready yet for that. So reliability is always a question we hear, right? Now, reliability, we're adding durability and lifetime. So that's really important. Electric motor side, I know you're not all in just electric motors, but something, some of you might be. We're still interested in non-heavy rare earth materials. That's what we're looking at currently. Now, in our current state, we don't look at induction motors or switch reluctance type motors anymore because of the torque pulsations and vibration. That will not be a problem for medium duty, heavy duty vehicles because the motors will be further away from the driver. And for the integrated drive, we're looking at power electronics and electric motor integration. I hear sometimes people talking about adding the gearing or the gearbox to it. Is that something we look at? Something like an e-axle, because that's something to be of interest. So there are changes coming, especially with these different class of vehicles we're going to work on. But it's really exciting. I think this is a great time to be working in electrification, and we're really excited about the possible opportunities coming up in this area. That's all I have for my presentation, and if you have any questions, I have time to answer them. I see, I think 12 questions seems like.
Yes, thank you so much, Dr. Ozpineci, for your excellent presentation. I know it generated a lot of interest. We had a great number of attendees also. Would it be easier for you? Why don't I go ahead and read off the questions and you can answer them?
Sure.
As I read them. So the first one we have in the Q&A is, what is the cost relation of the PLZT capacitors against film capacitors?
So I don't have the exact number for you, but they're more expensive.
That's a nice and concise answer.
Yeah, as I mentioned, sorry, Judy, one more. As I mentioned, something we're looking at, right? Right now, I want to use the best technology available. I don't really care about the cost right now because there's more demand, more production, the cost will come down. So that's the way we're looking at it. Something that will be in vehicles hopefully in 10 years.
Okay, great. The next question is, what do you think about PCB embedding integration in parentheses, power semiconductor chips embedded inside PCB layers?
Actually, we're looking into that too. I didn't say anything here, but if you wait for our AMR presentation, I'm sorry, it seems like, it's like shameless plug for this AMR presentation, these presentations, but we're going to talk more about PCB integration there. You're going to see some of these results over there. As I mentioned, if you cannot see them live, you can see them later, but we have some work in that area too.
Okay, and the next question is, since the auto industry is shying away from ceramic capacitors, does this suggest that they're going to shy away from other ceramic components due to risk of cracking, i.e. ceramic module and packaging substrates?
Very good question. So the main problem is with the ceramic capacitors, I don't think they've used ceramic capacitors for desealing. Okay, they might have used them in different areas, as long as, the important thing is the energy you store in the desealing, a lot of energy. So when there's a failure, it's not graceful. They love the film capacitors because film capacitors have self-healing features. Is a part of it fails and the rest of it you can still use. That's not what you can do with ceramic capacitors. So that's the main reason. Now, I don't think that's a problem for the substrates. We don't expect the substrates to be failing that way. Basically, I don't think there is a concern. I don't think they have a concern in the substrates for power modules in that sense.
Okay. The next question is one question about the inverter. Which one is better in EV applications? Symmetrical 6-phase inverter and asymmetrical or I think it's asymmetrical 6-phase inverter with a 30-degree phase shift.
Sorry, can you repeat that question, please? Or maybe I can read it here.
Do you see it? One question about the inverter. Which one is better in EV application? Symmetrical 6-phase inverter or asymmetrical asymmetrical 6-phase inverter?
Very good question. I don't have an answer for you for that. But if you'd like to, that's something you can contact my colleague Guja Su. He's the expert in that. He can give you an answer, or again, he's going to be presenting in a month. So if you'd like to ask him the question, he'd be more than willing to answer you.
Okay, great. And if you want to type that contact into the chat, I'm sure that participant might appreciate it, or the name, right, sure. The name of the colleague. And I would put that in the chat instead of the Q&A, just because I think the Q&A is only able to be seen by the host and panelist.
Okay.
So next question, what are the requirements from Semiconductor Switch side that are not met using present technologies?
Let me tell you what I want to have. I guess, a wish list. High temperature. When silicon carbide, when I say high temperature, I want to have 250 degrees C junction temperature devices. And if you have them, please let me know. Maybe, we're missing those things. And when first silicon carbide devices came out, that was the promise. We wanted to have high temperature devices. And I remember I worked with University of Arkansas, and then they packaged us some silicon carbide diodes at the time. And I put them in oven at 400 degrees C. I characterized them. So that was amazing. So that got me all excited. Of course, then we had the JFETs, and JFETs had the possibility of going to higher temperatures. Of course, they were normally on. And now we have MOSFETs. We love the MOSFETs. We work really well with them, but they can't go to higher temperatures as far as I know. So I think going to if we can get some higher temperature devices, that would really help us, especially with, we're trying to reduce the size and volume of these inverters. If we can get high temperature devices, we can build high temperature packages, reduce the amount of cooling we need, then, it would be easier for us to meet these high power density goals.
Okay, great. We've gotten a lot of questions about your presentation, which means it was excellent. So I'll try to get through as many as I can. And I wanted to say, if you have put a question into the chat, please do go ahead and also put it in the Q&A box, just so we can make sure we're getting through all of them, as many as we can, that we see them all. The next question is, what complications arise with paralleling wide bandgap devices?
So the main thing, of course, is you want to make sure that they are sharing the currents well, and MOSFETs do. So if you have a BJT type, negative temperature coefficient, then that would be an issue, of course. Now, having said that, MOSFETs, we don't have that problem. And having said that, I don't want to have like string of 50 die to achieve the current ratings, right? For me, I like the original IGBTs with the single die that can carry all these high currents. That made it easier to package, easier to handle. So that's the way I look at it. I don't think necessarily right now paralleling these MOSFETs at this point are a big deal at this point. But I think that's the main thing I look at, Victor. And by the way, Julie, I just saw a note here on the capacitor. It's one of our colleagues mentioned that's 50 times more expensive compared to film today. So, and just for reference for everyone, I want to highlight when silicon carbide devices first came out, they were probably more expensive than that. So that's the hope I'm keeping, that hopefully the cost of these devices will come down.
Okay, great. Next question is, how do you see the potential of outer rotor structure for induction machines, maybe with copper bars instead of aluminum?
Very good question. I never thought of that. Because the reason I didn't think of that was because induction motors, we've been avoiding because of the vibration issues. No, actually, it's more the cost, the rotor cost. One or other, when I went to school, when I went to grad school, I learned induction motors. I loved working on induction motors, but I didn't know that actually cost of the rotor was a main challenge. But it seems to be that. We can look at outer rotor motors with induction motors. I haven't really seen one, but I haven't really investigated them either, because I'm not a electric motors person necessarily. But that's very interesting, something to look at.
And the next question is along the lines of the outer rotor. Again, outer rotor motors are good for in-wheel packaging due to the design. The current EVs coming out are based on ICE vehicles. Would there be greater acceptance for skateboard design in the future, and what would drive that?
So actually, most of the EVs right now have the skateboard design. So you can just look at VWs, Teslas. You can just look at the Volvos. I think you can just look at them. They are all using actual skateboard design today. And the image I showed you of the Chevy Autonomy skateboard, actually that one had in-wheel motor designs. And that's something of interest to us. We're not looking at right now, but that's something I'm interested in looking at. So the main problem we're looking at right now with outer rotor motors, when we go to higher speeds, this is a challenge I want to make you aware of it, is, for example, we need bearings, right? We need the high-speed bearings, and now we're trying to integrate the inverter, so we need larger bearings so we can put the inverter inside the stator. So finding a large size bearing at high speed is a challenge. And once you find it, then there are some mechanical issues. There will be auto mechanical issues trying to figure out how we can actually spin this motor at 20,000 RPM. I'm not a mechanical person necessarily, but I have colleagues at the lab. They are actually looking at now how to make this happen, how to make these things operate at high speeds. Now, eventually, once we're successful with this, I wouldn't mind looking at the project for in-wheel motors using the technology.
Okay, great. It looks like we have time for a couple more questions. And the next one is, integrating the inverter and the motor with a medium duty or heavy duty axle is a big challenge to survive shock and vibration. I'm sorry, E-axle is a big challenge to survive shock and vibration. How do you plan to deal with circuitry on unsprung E-axles?
Thank you. Thank you for telling me challenges, because I need to find challenges for us to work on and solve. of course, once we start working on these technologies, that'll be something else. We will have to make sure that we operate. Now, at the lab, we have a lot of great facilities where we can actually look at shock and vibration tube and actually evaluate the whole e-axle on an emulated truck, for example. So there will be a lot more problems I foresee, trying to go to these medium duty, heavy duty vehicles. Something interesting to me, a lot of people think that you can just scale up the passenger vehicle drive systems for heavy duty, medium duty, but that's not going to happen. So there are also challenges people are not thinking of. And, thank you for bringing up another challenge here. These are the challenges, we're trying to compile and then actually show what these help us find the problems we need to solve for these things to be electrified.
All right. Yeah, sounds like we're getting some excellent questions through this. I think we have time for one or two more. The next one is, please highlight the scope of 3.3 kilovolt MOSFETs in fast charging applications. Very good question. So I have another talk on chargers actually, so I'll give you some input from there. So today, when you look at the chargers, fast chargers, you have a transformer connected to medium voltage, and the output of the transformer is 480 volts. Then you have a power converter that converts this AC to DC that you can plug into the vehicle. Well, we think that we need solid-state transformers that connect directly to medium voltage. So in that case, 13.8 kV or any lower level of medium voltage levels, if you want to connect your solid-state transformer there, then you need the 3.3 kV MOSFETs, or maybe higher voltage rated MOSFETs. If we can get the 10 kV MOSFETs, I know they have been worked on. So they would be on the grid side. And we want to switch them at higher frequencies. When I say that, because you might not be familiar with solid-state transformers, you have the 60 hertz, you convert to DC, then you convert to high frequency AC, where you have a high frequency transformer. So during this transition, you would need these high voltage devices switching at higher switching frequencies. Now, something else I want to highlight, I didn't talk about in this presentation, but wireless charging is something else we work on, and we want to connect directly to 13.8 kV or other medium voltage levels directly to the grid, because we want to go to 1 megawatt wireless charging using a single system. We're not talking about paralleling multiple units, a single system that can do that eventually, maybe in a few years. Now, these things are switched at really high frequencies. Today, we're demonstrating 300 kilowatt wireless charging through 6 inches at 85 kilohertz using silicon carbide devices. Silicon carbide devices make it happen. So when we go to higher power levels, and let's see if you'll be able to still achieve 85 kilohertz with this. But this is one area for silicon carbide and eventually gallium nitride to focus on, because we can't use silicon. We have to use these wide bandgap devices for these wireless charging applications. Okay, and we do have a few more Q&As that are still in the chat. However, we have reached the end of our time today for May's technical webinar series with Dr. Ozpineci. Thank you so much for your time today. I did tell attendees, we had several questions about whether this presentation would be available after the fact. That is typical of our webinars. We do send out a sanitized version to attendees, usually within a few days, a week after. So be expecting that in your emails and on those slides. I know that Dr. Ozpineci, I'm not sure if he put his contact info, but certainly his name is on there. So if you need to get in touch with him to ask him questions directly, he'll be available that way. And as always, our technical webinars are all posted on the PowerAmerica YouTube channel, which is accessible from our main homepage. In the top right corner, there's a little YouTube icon you can click on and access our channel with all past recordings of technical presentations. So thank you, Dr. Ozpineci. We really appreciate your time today, and I'll let you leave any final thoughts with the audience if you wanted to wrap up with anything.
Just want to let everyone know, this is, again, exciting times to work in electrification. And thank you for inviting me to give this webinar.
Thank you. And I hope everyone has a great afternoon. And we will be in touch with a copy of the presentation. Thanks again.
Thank you.